I'll be showing some new results as well. So this is the structure of what I'm going to talk about. I'm going to talk about what is Euclid and its main science goals and its secondary goals, and in particular the deep field science it will do in the North Ecliptic Pole, and then mining the very large data volume and complex data volume of Euclid and the progress that's being made there and challenges. So kick off. What is Euclid? So Euclid is it's a 1 meter class telescope that will be mapping about half the sky. It's launching in September 2022. The primary science goal of Euclid is dark energy equation of state via baryon wiggles and cosmic shear. And so to do this, it is mapping at least 15,000 square degrees with two instruments, the VIS instrument and the NISP instrument. The VIS instrument it's a broadband, very broadband visual imager. It's going quite faint, 24.5 10 sigma for an extended source. It's got a YJ and H near infrared imaging photometry going down to AB24, and near infrared spectroscopy. It's doing a slitless spectroscopy survey, all simultaneous. And it will also be doing a deep survey of 40 square degrees. And it's doing this in support of the primary science goals. It's a calibration field, in a sense. But of course, there's a lot of secondary science that comes out of these. In the all sky or nearly all sky survey, it'll be mapping with the red GRISM, and it's chasing H alpha emitters in order to get the baryon wiggles. And in the deep fields, because there's so much secondary science to be done, it will also use GRISM, okay, 0.9 to 1.35 microns. The deep fields, these 40 square degrees, they are in three fields. There's the Euclid Deep Field North, which is the North Ecliptic Pole. There is the Fornax field, which includes Goods South. And there is the Euclid Deep Field South, which you would hope would have matched to the Akari Deep Field South. Unfortunately, that was not possible. But the Euclid Deep Field North will be 20 square degrees with an inner 10 square degrees with an additional 3 times greater integration time. Of course, these fields have a lot of legacy data, so coming or forthcoming data. We have in the NEP, there's Toltec survey, there's the E-Rosita deep field, of course, Spitzer, Cyber, Scuba 2, Herschel already in hand, of course. The Fornax field, meanwhile, it's an LSST field. Unfortunately, the NEP is just too far north for the LSST. But it's also a Toltec and a Meerkat field, video and Veils and Spitzer and Herschel and Scuba 2, etc. in hand. And the Euclid Deep Field South, well, it's an LSST deep drilling field, but otherwise it is completely new. So that's a real pity. But it was unavoidable because the Akari Deep Field South has Alpha Doradus in it, and that made it unsuitable for this deep field. So it's a great pity. But I can't believe it's not Akari Deep Field South. So the launch is in September 2022, and there will be quick look data over 50 square degrees, about a year, well, December 2023, January 2024, and about a year later than that, there'll be a 2,500 square degree DR1, which will have a sixth of the final integration time per point in the deep fields, and the North Ecliptic Pole will be one of those fields. So that's Euclid. So it's doing this dark energy experiment, but the secondary science goals, personally, I think the most likely outcome of Euclid is we spend €1 billion discovering W is -1, and it will be principally remembered rather for the secondary science goals, which are amazing. There are so many things that it will be doing. So I'll just show you some pretty pictures here. You'll be getting morphologies of a billion galaxies, spectroscopic redshifts of tens of million galaxies, and the brightest line emitters in a third to a quarter of the sky, it will be getting 5,000 strong lensing galaxy clusters, and many, many more galaxy clusters on top of that. As an aside, are there any suitable strong lensing clusters in the NEP field? And that question is unanswered at the moment, and it's something I hope that our colleagues involved in the hypers PrimeCam surveys will be looking into. It will get 100,000 or more strong galaxy-galaxy gravitational lenses, and that will allow us to find rare, highly magnified lensed galaxies and quasars. When you have a very large population of objects, you're very good at getting rare populations. And another sort of rare population, lens population you'll get are these triple lenses, where you have 3 galaxies along your line of sight. So it's a lens by a lens of by a foreground galaxy. And because these things give you, the statistics on these things give you insights into geometry, this gives you omega matter on W to 10% on its own. And we call these systems jackpot lenses. It will get around 5,000 strongly lensed quasars and 1,000 spectroscopic quasars and lots more other things as well. So these are, in a nutshell, the secondary science goals of Euclid. So specifically, in the North Ecliptic Pole, what Euclid deep field science will be done. And there's quite a few things here, but I just want to focus on one particular area that I think is a winning science niche for the Euclid deep field science, particularly in the North Ecliptic Pole. And that is probing reionization with AGN, Lyman break, and Lyman alpha galaxies. So I've got a classic graphic here from a talk by Robertson. We go from the recombination era with the CMB through the dark ages, and then reionization happens redshift maybe 12, 8, 6. And then we get into the modern universe and present day universe. So probing this reionization population is well, it's a very high priority in many different facilities. But these different facilities don't have, well, some of them have particular disadvantages, and a particular disadvantage I want to talk about is a field of view. Because reionization sources should be strongly clustered on roughly degree scale. So I've got a simulation here, which I think this is a mass map at redshift 7. And on top of this, I want to show you the HST or JWST near-cam fields of view. And the cosmic variance there is 33%. And even with candles wide or good south and ERS JWST, its cosmic variance 20%. So really, you want to be probing scales much bigger than this. And especially if you look at the likely sizes of reionization bubbles, you could well imagine picking a highly atypical region. So you should be looking at degree scales. And on these degree scales, you want to be picking up Lyman alpha luminosity functions, distributions of objects with and without Lyman alpha, and so on. So this is what Euclid will be doing. It will be getting hundreds to thousands of ultra-Highrich of galaxies. And you can imagine using dropout techniques like shown here for the WISP survey. The numbers of objects that you will get is pretty uncertain. So I've got one of the leading predictions here from Bagley 2017. The prediction here for the whole 40 square degrees would be 1,800 objects at redshift 6.5 to 7. So that's tremendous. And so half that for the North Ecliptic Pole survey. But the thing to note is that that's based on detection of just 2 objects. So this is there's a lot of uncertainty in the numbers of objects that we will be seeing. Another population is the gravitationally lensed Lyman alpha emitters. So I've got a prediction here that we made a couple of years ago. This black curve is the probe of the luminosity function of the unlensed galaxies. And this is a pessimistic Schechter function. And here, the vertical line is the Euclid deep limit, and the gravitationally lensed galaxies are at the bright end here. So in this model, the gravitationally lensed Lyman alpha emitters would dominate Euclid deep at high redshifts. And there we would be expecting at least tens of objects. Okay, so that's the most pessimistic case. If the luminosity function is less steep, then you would get more unlensed galaxies, but you would still get the lensed population anyway. So this is an absolute minimum worst case. But the thing to note is that there are foreground H alpha emitters that are vastly outnumbering the surface density of these lensed galaxies. So filtering out the foreground populations is going to be a big challenge. So you can imagine a foreground H alpha emitter and being mistaken for a Lyman alpha emitter, for example. And these another problem with these gravitationally lensed populations is that the foreground lens spoils your color selection. So there's an example here of a gravitationally lensed quasar at redshift 6.5. The foreground lensing galaxy means the quasar would be missing from the usual color selections. So this is an additional problem if you're chasing these lensed populations. So there's a data mining problem here. To give you some more predictions for the deep survey, I've got a prediction here for the wide survey, strongly gravitationally lensed populations for redshift distributions, magnifications, magnitudes, Einstein radii, and I'm just going to switch over to the deep population. So the wide population has roughly 200,000 lenses with a detectable Einstein radius, and the deep survey, maybe I flick between them a bit so you can see the differences. I've tried to keep them on the same scale. The deep survey will be getting around 3,500 deep field lensed intermediate redshift galaxies. So there'll be a whole slew of strongly gravitationally lensed galaxies. And this simulation doesn't include the ultra high redshift populations. So we'll do that. So that will be, those are, I think, two highlights of the deep field science that will happen in the North Ecliptic Pole. So I'll just finish off with some words about mining the Euclid data. So finding these strongly gravitationally lensed systems has been, well, it's a data mining challenge. And so people have been simulating the Euclid data and then sending it to machine learning challenges. I've got one particular challenge entry that my grad student Josh Wild has made. This is the architecture of his convolutional neural net, and the convnets seem to be the leading technology here for doing this. I will just highlight that it means that there are 300,000 parameters in this. I mean, this technology is throwing parameters at this fitting problem, and this is a graphical representation of the architecture. You've got the Euclid data there, some convolutional layers and dropouts, and then the decision-making part, which is the fully collected layers. And here's an earlier challenge results with lots of convolutional nets leading the challenge. But I want to just highlight this one. This is a human inspection. Okay, this was this chap, Neil Jackson and his team, who heroically spent a few days eyeballing manually the 100,000 simulated gravitational lenses. The interesting thing is they did not win the challenge. The CNNs are doing better than humans. So why is that? So we wondered whether they were just getting tired. So we ran a Zooniverse experiment to crowdsource strong gravitational lens detection to see whether humans can actually beat artificial intelligence. And there is a very big community of citizen scientists who are very good at spotting gravitational lenses. So we ran this past them. The project is now finished, and it turns out that human volunteers give a more reliable lens sample, but are much less complete. They are nervous about clicking yes. So still we are in the situation, right, I'm nearly done, where machines beat humans. The Citizen Science Experiment 1, there was no better completeness or recall with more volunteers. And in the next experiment that's being planned, well, we will see how humans do. There is another challenge that has been completed, and humans are still not on top. So human vision is doing something different to machine vision, and that's a big problem. We don't understand how the CNNs are working, but we have to do better in order to find these ultra-high redshift populations. And I've got an example here of the true positive rate against false positive rate. Really, you want to be in this area here, and it's good, the sort of progress we're making with CNNs, but it's not quite good enough to beat this deep contamination problem at the moment. So conclusions: the opportunities for the Euclid deep in the NEP, it will beat the degree scale cosmic variance in reionization populations, unlike JWST and HST. And there'll be potentially hundreds or thousands of ultra-high redshift systems, lensed and unlensed. But how will we find the rare ultra-high redshift populations reliably in Euclid deep? That has yet to be done, yet to be worked out. And also, a question that we can solve now: are there any strong lensing clusters in the Euclid deep North Ecliptic Pole field? And that's something that I hope people will be getting into. That's everything. Thanks very much, and sorry for slightly overrunning.
Thank you very much. Okay, there are some questions on the draft. So, okay, from William, yeah. Have you done occultation experiments to see what your network sees?
So that's a really good question. So yes, we've been making activation maps and doing technology called Google Deep Dream, where you start with a random image and you start trying to accentuate the features that trigger a lens signal and just seeing what pops out. And people have done this for detection of cats or some, some such in images. And you find that pictures of guitars or pianos or something start developing whiskers and eyes and stuff, so you can see what the machine is seeing. So we've tried this on gravitational lensing, and the machine is seeing arcs, but not necessarily in a pattern that we would recognize as a gravitational lens. And the activation maps, it does seem to be zeroing in on arcs, but doesn't necessarily have the perfect rotational symmetry. So it's better at arcs in some places than others. So maybe the network needs a bit more training. But yes, we have been trying all of these things, and we still don't have an answer to why the machines are better at finding strong gravitational lenses.
Okay, there is another question from Tomogoto. What science requires 200,000 lenses?
That's a really good question. So I think that the thing I would focus on is that the opportunity for rare systems. You only get those with a very, very large sample. So, and this is also a machine learning question. So, for example, if you are interested in triple lenses and probing, getting more lines of sight through dark matter halos to get a constraint on halo profiles, for example, you need triple gravitational lenses, and you only find those with very large lensing samples. But you also need to check that your machine learning isn't going to somehow systematically select those away. And that's another thing we've been checking, and it does seem that our CNNs are able to detect the jackpot lenses. And people have also tried making cosmological constraints with lensing statistics. So looking for example, dependencies on dark matter equation of state on the redshifts of the sources and the lenses, but that turns out not to be a particularly sensitive cosmological statistic. People have claimed that in submillimeter surveys, but I don't believe it. So I think rare populations are the easiest win.
Thank you very much. There is another question, but please continue on Slack. Yeah, thank you very much. So, yeah.
Okay, thank you.